For years, AI development has chased two parallel goals: making computers read with OCR and solving the puzzle of visual text compression. While OCR is now commonplace, LLMs have hit a wall, the long context problem. As text inputs grow, compute costs explode quadratically, preventing AI from remembering entire books or long, complex histories. This is where the paradigm shifts. The DeepSeek-OCR model reframes the entire problem from an LLM-centric viewpoint. It asks, what if we stop extracting text from an image and start using the image itself as the compressed representation of that text? By proving a few vision tokens can represent thousands of text tokens, it's not just another OCR tool, it's a new architecture for AIMemory. So what is DeepSeek-OCR? It's not a standard utility. It's an advanced vision language model built as a proof of concept. Its core mission is to explore the limits of visual text compression, intelligently transforming dense documents and diagrams into a rich, highly compressed sequence of visual tokens. It's an efficiency bridge between high-dimensional visual data and sequential language processing. And this mission is accomplished through a powerful set of key features designed for engineers and researchers. Flexible resolution modes give developers fine-grained control, from a hyper-efficient tiny mode using just 64 vision tokens up to a dynamic Gundam mode for ultra-high resolution documents. You control the fidelity to compression trade-off. It also enables deep parsing. Trained on OCR 2.0 data, it goes beyond reading text. It interprets complex visuals, converting charts into structured HTML, chemical formulas into smile strings, and even parsing simple geometry. This is true document intelligence. This power is built on a foundation of data-rich training, utilizing over 30 million pages of diverse documents, and it's all driven by an LLM-centric prompting system, using specific tags to guide the model on exactly what action to take, like converting a document to Markdown or locating a specific reference within an image. These features unlock practical, high-impact use cases that go way beyond traditional OCR. Ultra-long context memory compression is the headline application. Imagine storing vast legal archives or patient histories, not as costly text, but as optically compressed images. This gives an LLM a near infinite and low-cost memory. It can even simulate biological memory decay by using lower fidelity compression for older context, allowing the agent to forget less relevant distant information gracefully. Its deep parsing enables high-throughput knowledge-structured extraction. This turns the model into an engine for automating knowledge graphs. Think of it as ingesting a folder of scientific papers and not just reading them, but outputting machine-readable data from every chart and formula ready for immediate analysis. And for businesses, this efficiency creates adaptive document intelligence platforms that can dynamically choose the most cost-effective processing mode for any document on the fly. So, how did DeepSeek AI engineer model to do all this? The magic is in its incredibly efficient two-part architecture. It's a two-part system. First, the deep encoder ingests a high-definition image and executes the optical compression, outputting a small, manageable group of vision tokens. This highly compressed data then goes to the MOE decoder. This is a mixture of experts model with a power of 3 billion parameters, but the inference speed of a much smaller one because it only activates a small fraction of its experts, about 570 million parameters, for any given task. This is the key to its balance of power and efficiency. The deep encoder itself is a three-stage masterpiece of intentional design. It starts with a perception component using window attention, which is memory efficient for processing dense inputs. Critically, a 16x token compressor then drastically reduces the data payload. This step is strategically placed before the final stage, which is a clip large component that uses computationally expensive global attention. This design avoids the memory blowouts common in other VLMs by ensuring the most expensive computation is only performed on an already compressed, manageable set of tokens. That's the theory. But how does this architecture perform on rigorous industry standard benchmarks? On the ThoX benchmarks, it proved the theory. It can deliver 96+% OCR precision at a near 10-to-1 compression ratio, a powerful proof of concept. But on the OmniDocBench, its practical dominance becomes clear. DeepSeek-OCR achieved state-of-the-art performance while using dramatically fewer vision tokens. For example, it outperformed GOT-OCR 2.0 and Miner U 2.0 using just a fraction of the compute, confirming that its efficiency isn't just a feature, it's a fundamental architectural advantage. Looking forward, the next frontier is embedding these capabilities into agentic systems. This transforms DeepSeek-OCR into a sensory cortex for autonomous agents that can navigate visual data environments. Its deep parsing ability would become a direct driver for action. An agent could read a financial report, extract key data from a chart, and autonomously execute a stock trade or generate an analysis based on its findings. The core challenge then becomes reliability and reasoning. An agent must learn to reason about its own perceptual limitations. This requires self-correction loops, like an agent deciding on its own to rescan a critical figure at a higher fidelity if its initial confidence is low. It must learn the meta skill of choosing the right tool for the job, a new research frontier for building truly robust AI agents. DeepSeek-OCR is not just a research paper, it's an open-source tool you can use right now. The project's code and model weights are available freely on GitHub and Hugging Face's released under the permissive MIT license. The repository provides detailed setup instructions and scripts to get you started with either transformers or the high-throughput VLLM framework. Of course, there are limitations. The model's near lossless compression has a hard boundary. Accuracy drops significantly at compression ratios above 10x. Future work will focus on validating this paradigm beyond OCR with techniques like needle-in-the-haystack testing, pushing the boundaries of general-purpose long-context memory. How would you apply this technology? Head to the GitHub repository to explore the code, experiment with the different resolution modes, and start building. Let us know your most creative ideas in the comments below, and if you found this deep dive valuable, don't forget to like and subscribe for more content on the future of AI.